So for example, if you have an example, determine the Hamming code. You can try yourself. Determine the Hamming code for the database 10110, 10110. So this is D1, this is D2, this is D3, this is D4, this is D5. And using the OR packet, determine the Hamming code. You have to determine, sorry?
Shouldn't D1 be LSB?
Yeah, just for example, you think that this is D1 and D2 and this is like this. That's why I mentioned. So this is D1 and this is D5. So D5 is the LSB and D1 is. So don't worry, just put. So you have to make a table here, put accordingly. So determine the Hamming code for this database using OR parity. Please try yourself and give me 3 minutes to 4 minutes. I'm coming.
Should we have 4 databases?
It's now 5. So you have to calculate how many packages you require. Okay? I'm coming back. 3 4 minutes. If it is even parity, we should try to find out even number of ones. Yes, sir.
So the table on the left just tells us which parity bit corresponds to which data bit.
Which data
And
bit?
then to select the parity bit, we just look at the corresponding data bits.
Yeah, data bits.
So if it's an even number of ones for the corresponding data bits, we would make the parity bit a 1
One.
to make it odd.
To make it out.
Yeah.
Exactly. So this table will showing us which position, which data bit we'll choose. Then we'll choose the data bits and to try to count the number of ones. As you're looking for odd, if it is even, we'll make it odd. If it is already odd, we don't need to make it, put anything.
Sir, I can also write P1, P2, P4 and P8.
P1, P2,
P4 and P8.
you can write. But it's better, we have 4 parity bits, so 1, 2, 3, 4. That's what we write. The position is 1, 2, 4, 8. Position. Because we have to set the position as well. Okay? Sorry to make you confused first. Now it's fine, everyone? Will you move forward? The next one is the parity checker. So we have set the data, now we have to check the parity bits, right? If you go to slide number 26. So for example, we have transmitted a bit. Transmitted this signal. The signal is 111. Sorry. Transmitted bit is 1010010. This is including the parity. Okay, we transmit it. But in the receiver side, we receive, for example, 1110010. So this is my bit shifted or flipped. So according to our Hamming code, we can detect as well as we can correct. So at least we can find out which position bit is changed, right? So in the parity receiving side, we have the parity checker. We have 3 parity checkers because we have 3 parity bits. It is C1, C2, C3. Same C1 will go for 3, 5, 7 and P1. C1 corresponding to 3, 5, 7 and P1. C2 corresponding to 3, 6, 7 and P2. And C3 corresponding to 5, 6, 7 and corresponding to 3. Of course, at first we need to know whether it is even parity or odd parity. So it's an even parity. So we send data in the receiving side, we'll try to find out whether number of one is even or odd. Okay. So what we can see here, for C1 it is 3, 5, 7, P1, right? So 3, 5, 7 means data bit 1, this means this is D1, this is D2, right? And this is D3, if I'm not wrong, right? This time D1, D2, and sorry, D4. Yeah. D1, D4, D4. Yeah. So what we have here, so this is P1, this is P2, this is D1, this is P3, this is D2, this is D3, this is D4, right? Correct? P1, P2, D1, P3, D2, D3, D4. So 3, 5, 7 means positions.
D1.
So 1, 2, 3, 4, 5, 6, 7. So D1, D2, D7. So what we can see here? Even number of ones or odd number of ones? For C1, even number of ones. So we are looking for even parity. So if we get the even number of ones, that means there is no error. If there is no error, this parity checker will send 0. That means here we don't have any errors. Then we'll go for the parity checker 2. Parity checker 2 is corresponding to 3, 6, 7, P2 itself. So P2 itself, 3, this one, 6, 7. So 3, 6, 7 is also what? Odd number of parities. 1, 2, 3. But we are looking for even number, right? So we are looking for even, we are having odd. This one, and this one. So when there is a wrong error, it will send 1. Okay? Then we'll go for the third parity checker, C3. It is corresponding to 5, 6, 7, P3. 5, 6, 7, P3. So these 3 and the P3. So again, we have even number of ones, right? Even number of ones. Sorry, odd number of ones. 1, 2, 3, 5, 6, 7. So it will give you this one. So whenever it will give you 1, 1, 0, this is actually corresponding to what? 6?
Binary.
1, 1, 0 corresponding to 6.
6.
So we have a
6 is
bit
the
error at position number 6.
standard. And we have to change it.
Yeah. So we can know that this bit is actually flipped. So you just change it. Okay. So again, I'm repeating here. So this data is sent to us, and this data is received. We need to check in the receiving side, and the checker is known as parity checker. So as this, we have a 3-bit parity bit, so we have 3-bit parity checker. So it will be C1, C2, and C3. Again, here also C1 corresponding to this position number 3, 5, 7, including the P1. For the parity checker C2, it's corresponding to 3, 6, 7, including P2. For parity checker 3, is include 5, 6, 7, including P3. If it is an even parity, that means the number of ones should be even. So we need to find out whether we have even number of ones or not. So for first one, 3, 5, 7, P1. 3, if I take another color, 3, 5, 7, and including P1. So we have even number of ones, so it's correct. So it will generate 0. For C2, 3, 6, 7, P2. Again 3, 6, 7, and including P2. So now 3, 6, 7, P2, we have, which one? 3, 6, 7, 3, 6, 7. 1,
That's a transmitted,
Sorry.
not the received.
1, 2, 3, right?
Check the
We should check the one.
Sorry, what I mistake here?
You're using the transmitted, not the received.
Okay, so it's an odd, right? You can see the 3, 6, 7, 3, 6, 7. This one.
We should check on the receiver side, right?
Oh yeah, sorry. 3, this one 3, right?
Yes.
3, 6, and 7. And including P2. Now we have 1, 2, 3. Odd number of ones. So it is a wrong. It will generate 1. Then finally it is 5, 6, 7. 5, 6, 7, including P3. So it is again 1, 2, 3, 3 odd numbers. So it will generate 1. So this is how we can, by using the Hamming code, we can detect and correct the errors. But there is a drawback or the limitation that it can detect only one bit here, one error, and can correct. But if there is a more than one error, one bit error. So if you want to decide or try to find out more than one bit error, we need to add another bit. It's known as extended Hamming code. It is known as extended Hamming code. If you go to the next slide, slide number 29, you can see slide number 29, it's an extended Hamming code. In the extended Hamming code, for example, for the 7 for Hamming code, we have already 7 bits. 1, 2, 3, 4, 5, 6, 7. We have already 7 bits. Okay? So it is P1, P2, D1, P3, D2, D3, D4. Now they will add another bit, extended priority bit P. So for example, this extended Hamming code can detect 2 bits of error, but it can correct only 1. It can say that, okay, the bit position 7 and bit position 5 have been flipped, but it can change only, correct only 1 bit. Okay. So for example, if you go to the next slide, slide number 30, here's an example. We send a Hamming code. The Hamming code is 1010010. Then we have an extended Hamming code. So we are trying to make it even parity. So in the Hamming code, we have how many number of ones? 3 ones. So to make it even number of Hamming code, we put in the extended Hamming code, put another 1. So now it becomes even parity. Now we send it to our transmission line. In the receiving side, it received, you can see 1110010. Okay? In the receiving side, it received 4110010. So, okay. So in the receiving side, it will check whether the number of ones is even or odd. So here we'll check 2 different things. The first one, what is the number of ones? How many ones we have received? It's supposed to be even number of ones. The first, they checked, they found that it is overall parity bit is odd. Okay, overall parity bit is odd. Then they check with the parity checker will check the same way, C1, C2, C3. So if they found any error, that will be non-zero. Because when there is an error, they will give you 1. That is non-zero, right? So C1, C2, C3 will be non-zero. Okay. So when it will happen, when the overall parity is odd and C1, C2, C3 is non-zero, it means that there is 1 error. There is 1 error. So 2 things. One is number of ones. Second thing is parity checker. Is it generating zeros or non-zero? If it is generate 0, that means no error. If it is generate 1, there is error. So if it is non-zero and the number of ones in the parity bit is odd, it will mean that there is 1 error. Okay. If you go to the second case, in the second case, I mentioned that whatever we transmit, we receive the same signal. That means no error. If there is no error, what will happen? The parity bit will be even, total parity bit will be even, and C1, C2, C3 will generate 0. That means it is no error. It's very simple. The third case, if there is 2 error, if you look at the slide number 32, if there is having 2 error, for example, the receive bit is now 1110010. So that means we have now 2 bits actually flipped. So what will happen? If you count the number of ones in the receiving bit, the number of ones is how many? 1, 2, 3, 4, even. So here number of ones is even. But the parity checker will generate a non-zero. because here there is an error. That's why parity checker will generate a non-zero. But my number of ones, the parity, even parity or parity number of counts of ones is showing even number. That means there are two errors. So if you can remember in our last lecture, we said that normal checker, parity checker, normal parity checker, not the Hamming code, if we have the even number of errors, we cannot detect. If you have the odd number of errors, we can detect. But with the Hamming code, we can even detect the even number of errors. But we can correct only one position. Okay, another thing can happen. This is my extra bit, right? Extended Hamming code. And we put it 1 to make it even. It can be also error. It can be also get flipped from 1 to 0. So if it is happen like that, we will see, we can identify it by, in that case, whenever the overall parity bit will be odd, but parity checker is 0. So parity checker will check in the data bits. So when the parity checker bit is not 0, is a 0, that means there is no error in your data bits, but the overall parity bits got into odd. That means this number actually flipped. So this is how we can correct and detect the error in the transmitted receiving bits. Okay? So this is all about this extended Hamming code. Of course, if you want to try to find out more error positions, so we need to extend more bits, but it will cost us the bandwidth. So this is also one of the major problem of the digital communications. In the analog communication, the major problem is the noise, because the analog communication we use the amplitude modulation, we send the amplitude signal, the varying signal. So noise is also an amplitude. So if that was easily get interact with our signals. On the other hand, in the digital communication, we don't have noise such that, because we can easily detect there is no signal, is only 0 and 1. But the problem is the bandwidth is very high. It's more than twice of the analog signal. It requires more bandwidth. So more bandwidth means more money you have to cost. So, but it's good because there is no noise. It is noiseless, noise-free. We can send data. Otherwise, you need to send it back to correct it or some other problems. Yeah.
The question is, the flipping happens. Is it due to the noise, right?
Yeah.
So it's not noise-free to be
No,
at the
you
point.
we can actually detect, but it's rare because it will. Is how it will be. Most of the case in the digital communication, we did the optical fiber. Okay, so the noise can generate because it is related to the clock timing cycle. So maybe one can be slower or can be faster in nanosecond.
Okay.
So if you can synchronize this transmitting and receiving clock, so it will be actually noiseless, almost. Because they are getting zeros and ones by time frame, right? So if you can control this time frame, so it will be automatically
The clock
0 and
speed.
1. Yeah. It is not created from environmental. But in case of amplitude modulation or the frequency modulation, it's totally environmental. Like from the surface, from the air, from the temperatures, everything, so many things are there. Because when you send data to the microwave antenna, it is in the free space. In the free space, we don't have any control with the temperature, right? Sometimes there will be fog, sometimes there will be rain, so the noise will be there. But whenever we're sending data to these optical fiber things, the bits are there. So bits are 0 and 1. There is some threshold level to detect logic 0 to detect logic 1. We'll see in future. So from, for example, from 0.2 volt to 0.8 volt, everything is 0, logic 0. Then we put a gap. Then we decided from 1.5 volt to 2.7 volt, everything is logic 1. So there is a very big threshold level. Okay? Then we'll move to the next slide. I upload another slide. So there is another few other Hamming code known as 1511 Hamming code, 3126 Hamming code. That I mentioned that if you need, we need to send more and more bits. So we need to increase the number of parity bits. 1511, 3126. These are the different kind of Hamming codes that we have. if you now open the second lecture, so it's logic gates. We already know what the logic gates is. So I just go through very fast. So whatever we want to design, any kind of sensor, we need this logic gates, right? So this is the digital electronics. And there are three basic logic gates: AND gate, OR gate, and NOT gate, we already know. And then we have so to identify logic high, that means 5 volt or 2 volt or 3 volt, as I mentioned, is a logic high, or logic low, 0 and 1. Logic low is from 0 to around 0.8 volt, we decide, right? So in the logic gates, we have the three basic logic gates: AND gate, OR gate, and NOT gate. Then we have two universal gate. One is the NAND gate and another is the NOR gate. By using the NAND and NOR, actually we can implement any kind of Boolean expression. In addition to those gates, there are two more gates, very important gates. One is the XOR gate and another is the XOR gate. This XOR gate and XOR gate is very much important because whenever we design the addition, subtraction, adder circuit, we need this XOR gate and XOR gate. Even for the gray code conversion, right? For the gray code conversion, we need this XOR gate. Okay. So I know, just I put these things, you can go through this. The output is high when both inputs are high for the AND gate. And this is the symbol. You can make 3 inputs AND gate, 4 inputs AND gate, 5 inputs AND gate. But if you keep increasing your AND gate, it will actually increase your complexity of the circuit as well as the power consumption. Whatever we see in, this is an IC, right? We call it an IC 7474 IC, 747 IC. This is an AND IC, this is an OR IC. But inside, what we have analog electronic circuit. This is all about the transistor inside, right? The transistor. So usually we can use the BJT transistor or the MOSFET transistor. But those transistors are related to temperatures, are related to the capacitance. They form a capacitance. So if we increase the number of input signals, the capacitance will increase. It will reduce your speed. So those are the things we need to keep in our mind. So that is not like, yeah, you can make a 5-input NAND gate. You can, but we usually do not do. Otherwise it will increase your complexity. Rather we should just put 3-input NAND gate, then take out the output, then give it to that another gate. So it's possible. But the output of the AND gate will be high when all the inputs are high. On the other hand, the OR gate is doing the summation, A plus B, right, or B plus A, and the outputs will be low when both inputs are low. Very common thing. Here also we can add any number of inputs. And then inverter circuit, whatever you give, if you give 0, it will create 1. This is inverter. Okay. The NAND gate. The NAND gate is just opposite to the AND gate, right? The output will be low when all the inputs are high. Good. Then the NOR gate is output is high when both inputs are low. For the NOR gate. This is opposite to the OR. Okay. So now, this is not the meaning. So what is the important thing is, what is the application? For example, for a home safety and protection system, which type of gate we should use? That means you have, for this room, you want to make a protection that we have 2 doors and we have, 1, 2, 3 doors and we have 3 windows. So to make it protection, safety and protection, which type of gate we should use? AND gate or OR gate?
AND gate.
AND gate, okay. So AND gates will be high when both inputs are high. That means the thief can open one door, he don't need to open another door, he can easily enter. Is it okay? No. We need to use the OR gate because it will generate high when any input is high. If you open any door, it will generate high. If you use the AND gate output will be high when all the inputs is high. So we have 6 entrances. So if any one entrance is high, the alarm will not work. So alarm will turn on if you use the
AND gate.
OR gate. By using the OR gate, we can. So for example, if I can draw, so this is the one window, two window, and the one door. Then we give the connection to the OR gate. N1 is open, any input is high, output will be
High.
This is how. So this is just a simple example. So you need to prepare yourself for the example. Maybe I will give you the scenario. You have to design the circuit. How you can design the circuit. The second one, applications of an AND gate. One of the most common application of AND gate is in our car, the seat belt. In the seat belt. So if you turn on your engine, the alarm turns on, right? Toot, 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 toot. Why? They ask you to put the buckle of the seat belt. So that means they need to make the signal will be gone when both are high.
High.
When both are high. So that's why the input, the gate, we should use the AND gate. And sometimes we can see that in most of the car actually, after 30 seconds, the alarm goes
Turns
down.
off.
So if you use a timer circuit for 30 seconds, it will, nowadays it actually keep continuing give the siren.
At least 2 or 3
Yeah,
minutes.
keep continuing the siren. So this is the use of AND gate. So that means any input is not, the output will be high when all the inputs are high. Okay. So this is the application of AND gate, a seatbelt alarm system they use. Okay. Now the NAND gate. Okay. So NAND gate, from the, if you look at the truth table of a NAND gate, what the NAND gate said?
The inputs are
It's the opposite of AND gate.
AND gate.
That means the output will be
zero.
low when
When
both
both
inputs are
high.
high. This is the AND gate. So what about the OR gate? OR gate is also same. OR gate is the same. So we can say that from the viewpoint of a NAND gate, it can be used for an OR operation that requires OR or more input to produce high input. So it is something like that. If I draw the logic gate, maybe it will be easy. So A, B, and Y. 0, 0, 0, 1, 1, 0, 1, 1, right? For the NAND gate, it will be 0 here, otherwise all are 1 for NAND, right? Opposite to the AND gate. And for the OR operation, we can see same 0, 0, 0, 1, 1, 0, 1, 1. It will be 1, 0.
So
Sorry.
0, 1, 1,
Sorry.
1,
0,
1, 1.
right? So we can implement, or we can think that, so we already know the NAND gate. This is the NAND gate. Sometimes in some book they give bubble, sometimes they don't put bubble, okay? So we can think this is something like this, right?
Yes.
The same thing. Okay. So this aspect of NAND operation is referred to as negative OR. This is known as negative OR. Negative OR. Okay. So what is the application? What we can use? For example, I give you the scenario. A manufacturing plant uses 2 tanks to contain a certain liquid chemicals that are required in a manufacturing process. Okay, 2 tanks. Each tank has a sensor that detects when the chemical level drops to 25% of the full. The sensor produces a high level of 5 volt when tanks are more than 1/4 full. More than 1/4 full, it will generate a 5 volt. When the volume of chemical in a tank drops to 1/4 full, the sensor puts a low level of 0 volt. It is required that a single green LED on an indicator panel show when both tanks are more than 1/4 full. Implement this function using a NAND gate. So this is how I will give you the, so you have to understand, you have to just draw the circuit. So again, I'm saying you, see in a manufacturing plant, we have 2 different kind of chemicals. So we have tank of 2 different kind of chemical tank. Okay? The first thing they said that each tank has a sensor. Each tank has a sensor. For example, if I draw a sensor here, this is a sensor. Okay, has a sensor, and that detects when the chemical level drops to 25% of the food. Drop to 25%. Fine. The sensor produces a high level of 5 volt when the tanks are more than 1 quarter full. So high when they are okay. When they are fullest, they will create, for example, this is high level. This is high level. Okay? So that's so the sensor produces a high level of 5 volt when the tanks are more than 1 quarter of full. When the volume of chemical in a tank drops to 1 quarter full, the sensor put a low. So it will be low when they will be low at 0 volt. It is required a single green LED on an indicator panel. Show when both tanks are more than 1 quarter full. So if I draw this one, as I mentioned, it is a AND gate, right? Application of AND gate. 2 input AND gate. So here, then in the indicator panel, we have a green LED, right, like a diode. I have a diode here. So we know the diode symbol, right? Is it okay? Then just a protection resistor, then the port. So it's a green LED.
This will turn on when it's 0.
Sorry?
This will turn on when it's 0. It's low.
So it will give, the sensor produces a high level of 5 volt. It will turn on 5 volt. That means when it will be a 5 volt, it will be turned on.
So we should put the diode in.
Okay, that's why I want to know. So what will happen here? So that means this is the NAND gate, right? And the NAND gate is output is 0. When?
Both are high.
Sorry, it's a NAND gate, not AND gate. I am talking about the NAND gate. When both are high. So when both are high, it will create low. And this low is connected to the negative terminal.
Then it will glow.
Shows high as a result.
Yeah, when it will be high. As I mentioned here, each tank has a sensor. The sensor produces a high. Look at, I will read the question again. The sensor produces a high level of 5 volt when the tanks are more than 1 quarter full. When more than 1 quarter full. So it's sensing more, it is more. It is, if it is less than 25%, then it will be here, right? So it is already more. They will create high. When both input is high, output is low.
Low.
And this low output is connected to the negative terminal of the diode, and positive terminal is connected to the positive terminal. So diode in on condition, we already know. If the diode is in forward bias, the diode will be turned on. If the diode is in reverse bias, it will not turn on. So that means when any of the tank goes down, it will create low. If it is low, it will be high. If it is high, it will become open because it's a reverse bias. Okay?
So the
Yes.
upper one is the VDD, right?
Yeah, VDD.
So that's low. It's going to the negative.
So
one.
here, what we need to do
Got it.
for the negative terminal, so you have to choose here very less low voltage. Of course, as it is a 5 volt, maybe you have to choose a 2 volt something, just to turn on the diode. Otherwise, for example, as you are saying, this is a reverse bias. When it will be reverse bias, this terminal should be lower potential, at lower potential than this terminal.
That means this should be at least 2 volt and that should be 5 volt. Then it will glow.
Yeah.
Got it.
It's not supposed to be that you need to connect to the negative terminal. It should be in the lower potential. Yes, the potential difference. Okay. The last example, if we have the NOR gate. The NOR gate, we use this NOR gate, a very simple gate. The NOR operation is just opposite to the OR operation, right? NOR operation is opposite to the, opposite to the OR operation. So NOR gate, the symbol is simple here with a bubble, and that implies going to AND operation, negative AND, we can say. Okay, anyway, we can use this NOR operation in the aircraft. In the aircraft, we had 3 gear system. So I read it slowly, try to understand. As a part of an aircraft functional monitoring system, a circuit is required to indicate that status of the landing gear prior to the landing gear. So we have 3 wheels, so 3 landing gear. A green LED display turns on. A green LED display turns on, that means LED will be turned on if all 3 gears are properly extended. When the gear down switches has been activated in preparation for landing. So the green LED will be turned on when all the 3 gears extended. A red LED will display if any of the gears fails to extend. So there will be 2 LED. One is the green and one is the red. The green LED will turn on when all the 3 gears properly extended. And the red LED will display if any of the gears fail to extend properly prior to landing. When landing gear is extended, its sensor produces a low voltage. When landing gear extended, it produces low voltage. So when it is extended, it producing low voltage. Again, green will be turned on when all the gear, right? All the gear properly extended. And red will be turned on when any of the gear not extended. Sorry, for my poor handwriting, I hope you can still read. So this is the condition. And now, if it is all the gear, if the gear is extended, the sensor produces a low voltage. And when landing gear is retracted, it produces high voltage. When retracted, it produces high voltage. Implement the circuit using the NOR gate. You have to
There will be
implement the
3.
circuit using the NOR gate. Okay, let me draw for you.
The first one is NOR.
Sorry?
NOR. The green is the NOR for all the inputs because it's A bar, B bar, C bar. So it's just 2 nuts and it becomes A plus B plus C whole bar. So it's just a NOR. And the other one is just the inverse of that.
Yeah. So, yeah, he's correct. So let me draw these things. So we have the landing gear sensor, 3 landing gear. This is the 3 landing gear, 3 wheels of the aircraft. So we have 3 output.
3 input.
Sorry, 3 input. I'm sorry. 3 input here.
Sorry.
We can take input here, input here. Okay? Now we have to use this one. And we can input this one. Then we have the LED. Here we have the LED. So this is the red one. This is the red.
So retraction will be high, so it will grow. Wait.
So let me discuss these things. So landing gear sensors are had. Here we have this landing gear sensor, extended low and retracted high. Okay? We have red and green. So power is applied to the circuit only when the gear down switch is activated, right? Use the NOR gate for each of the 2 requirements. One NOR gate operates as a negative AND to detect a low. Negative AND to detect a low. Okay? To detect a low. And the second one, remain retracted when the green down switch is activated. When one or more of the landing gears remain retracted, the resulting high from the sensor is detected by the NOR gate. Which is the NOR gate? This one. And which produces a low output to the turn on to the red. So here they need to produce low output, right? This is connected to the negative terminal. So it will create a low output. When? When we extend it, right? So this is how we can design. So these are the few examples, as I mentioned that. So this will be the scenario, maybe I'll give it to you. You have to read and try to design it. The time is over, right? Today actually have lost so much time. I'm sorry for that. So anyway,
Are you gonna post your
Handwriting?
notes for the examples?
Those examples. If
this
you-
one? Okay.
So that we
This
can,
is actually, I just got it from the reference book. I already uploaded the reference book, right? The reference book is there. You can find that. Also, I can upload this to this. I
okay.
have already uploaded the reference book. I just write
It's
down
in the
this.
examples, right?
Yeah.
In which chapter?
It will be the gates, the logic gates. Maybe chapter 3 or chapter 4. Logic gates.